All right, let's get started. Hi, everybody. Good evening. Welcome to our March meeting, San Francisco Dynamo User Group. Who is here for the first time? Great. Hope we can engage you enough to have you come back. We meet once a month, usually the second or the third Wednesday of every month. And on the screen you have how you can find out our activities, our blog, Twitter, and if you have any interest in becoming a speaker, send us an email at SFDUG.coordinator@gmail. My name is Cesar Escalante. I am the coordinator of the group, and I'm the manager for HOK. And let's do some announcements, and then we'll head this to the main featured speaker. So we welcome Brent Young and Ben Bushmann of Building SP. They're here to talk and demonstrate Dynamo applications for MEP systems. Thank you for being here. Few announcements. We have a new committee member in Sam Kamasevi. I don't think he will be able to be here tonight, but he has stepped up to become our new campaign manager, so he's going to be helping us send those emails that you receive on the inbox every month. Thank you, Sam. We are also working on getting finalized our agenda and schedule for the design script workshop. It's most likely going to be on April 28th. Location to be determined. It's a workshop open for about 15, 18 people. If you're interested, to stay tuned to our announcement. It's going to be a workshop of about 6 hours. It's going to be taught by 4 of the committee members, including Enrico, who's sitting here next to me. And the idea is to, there isn't any class on design script anywhere. I mean, all we have is just manual, and what we want to do is expand it a little bit and make it more accessible to everyone. So this one-day workshop is open to anyone, and so April 28th is Saturday. It's most likely going to be either at the AIA or here. We have a new sponsor. Thank you, Gensler, moving forward. And that's my friend, Cody from Gensler. Gensler has kindly agreed to provide us with new communication service. And starting next month, we're going to be using Google. We're going to stop using WebEx. This is giving us a lot of problems. And start using GoToMeeting. And thank you, Chancellor, for that. Thank you, IDA, for the food and beverages, as usual. And always calling for speakers. Next meeting, we're going to host remotely Conrad Saban. And we're going to talk about Mandrill for Dynamo. If you haven't heard about Mandrill, it's a package that enables us to create visualization of data mined and extracted from Revit data. So it's going to be a very good presentation. And from time to time, I like to greet some of our fans that are connected online. And this time, I want to thank this person in particular, Alberto Chono. He has consistently connected to our group since we started, and I don't know if he's online, but he is based on Italy, and it's 2 a.m. in Italy, and he's always connected from there at that time. So thank you, Alberto, if you are online.
It's dedication.
Yeah. One more announcement. Oh, did I miss that? Oh, I had one more announcement. I think February 22nd, if you go to the Facebook page of the Institute of Computational Design, they're going to broadcast a 3-day workshop for free on C# plus development for Grasshopper, and it's going to be streamed live along with the data sets and the files. So it's going to be amazing. So if you just go to the Facebook page, Institute of Computational Design in Stuttgart, they just have announced it. So stay tuned. Okay. With that said, I want to welcome again Brett Young, Ben. Thanks for coming here. They are with Building SP. They are doing great things with Dynamo applications for the MEP side. We want to have more exposure of Dynamo on the MEP front, so we might have them back again. So I'll make you the presenter.
Okay, great. So my name is Brett Young. I'm with Building SP, and I'm joined by Ben Bushmann. And we really want to thank HOK and Cesar for hosting us and for all the other sponsors to make today possible. So today we'll be talking about how to do Dynamo with MEP systems. And my job here on the front end is to kind of give you a background on the company and the products we have. So you can have a context for the demonstrations that Ben will give on how to apply it to projects that you have. Just so you know, because I think that'll come up as a question, is we'll post all of our Dynamo scripting to our website, so you can download it and take a look at it and use it as you see fit. And if there are other additional files that you need, like our sample models and things, we can provide that to you separately. So just get a hold of us on our website if you want to do that. So I can give you a little bit of background about myself. I worked for a general contractor for 9 years, and then I started a BIM consulting company. And 2 years ago, we started Building SP, and we've grown that team and have been building products as a software development company to go off and tackle computational approaches to MEP design and planning. And Ben, if you want to talk about yourself.
Yeah, so I started Building SP almost 2 years ago as well. Came from the electrical design world, so I'm an electrical engineer by training, and acquiring knowledge about all types of MEP is what my job is.
So kind of the outline of what we're going to talk about. Again, my job is to give you a background of the products we've integrated with Dynamo, and then Ben will go over and talk through a couple of examples and show you the code and run the code to show you what it can do. And then I'll finish up by taking a look at one of our products that we are planning to integrate into Dynamo and get your feedback on how you would like to see that happen. And so we'll show you what that product is, and then we'll talk about what you'd be looking for if we were to integrate that into Dynamo. Really want to thank everyone, online, here, or otherwise, because our industry really needs people to go and tackle hard things, and you can't go off and tackle things like big data and computational BIM and AI and machine learning if you first don't really attack automation in a hard way. And if you look across at everything involving those types of bigger computational concepts like big data and machine learning, it always involves automation first. And the Dynamo community is the biggest group of people who are kind of focused on doing automation for our industry. And so, we're supportive as a company of everything that you guys do, and we really appreciate the enthusiasm you guys have for Dynamo and what it actually means. So, huge thank you to you guys, and it's really evident at AU, you feel the energy of Dynamo, groups like this and others out there. So, kudos really to what you guys do. Kind of the origin of what we do at Building SP, I wanted to attend a conference for computational design, and I went and looked, and no MEP firms were going to go. And because of that, I started looking at what it meant to do computational design for MEP, and it eventually led to a phone call to a guy in Australia who had written his PhD on how to auto-route wiring harnesses and hydraulic lines across the F-35 fighter jet. And so I started talking with him, and we noted the similarities between what he does and what he was doing and the building industry. And he ended up coming on board, and that was kind of the origin where we kind of all started for what we do. His code is still being run in what we do today. So the F-35 code, you know, kind of that original code base is still in the products that we have. Since then, we've built a company. We have programmers who are professional programmers, and we have people like me and Ben who are more on the domain expertise for AEC. So we're a combined company of both programmers and people from industry. And then kind of quickly walking you through the two products that we have. GenMEP is an auto-routing tool for Revit. You define a start point and end point, and it'll auto-route between the two. Ben will go through a bunch of examples showing that work and showing you what that can do. And then Clash MEP is a real-time clash detection tool for Revit. So as you're modeling within Revit, you get real-time interactive feedback on what you're clashing with as you model. And that's a product I want to show to you and get your feedback on how it could best integrate into Dynamo. The technology of what we do is pretty technical, and if you guys want to talk afterwards about what that means. But generally, whenever we do anything involving our tools, we create a voxel space, and then we route through that maze. So imagine building a Minecraft building from a Revit model, and then we use that to either auto-route or do clash detection against it. And then there are a bunch of algorithms that we've customized and adapted to be in 3D and to be appropriate for buildings and to have enough intelligence to look like a conduit or look like a duct. And that's a picture of what it kind of looks like when you kind of go under the hood and kind of take a look at everything. So with that, I'll turn it over to Ben, and he can walk you through demonstrations of first, how to do generative design within MEP and how you come to an optimized outcome, medical equipment tracking, including the automatic placement of electrical outlets for that equipment, and then congestion complexity characterization with Dynamo.
Thank you, Brett. Thank you, everybody. I'm probably going to sit, but I wanted to thank everyone for having us here. Caesar, that's very nice for having us tonight. I'm going to walk through these three examples. Feel free to ask any questions as you see them. I want this to be a technical discussion. If you have a question about what I'm doing, or if you have a suggestion to say, hey, those 5 nodes can be replaced by 1, tell me. Because just like everybody else, like Brett said, we have professional software developers, and then I touch Dynamo and play with it and make these things that are fun and helpful for what I'm doing day to day. But I'm not a professional software developer. Dynamo helps me kind of cheat that, right, and get automation happening in a quick way and test it. So every feedback is good feedback for me. All right, so generative design. So what we're looking at here is a typical office building with a drop ceiling and MEP systems above the drop ceiling. We have a lot of duct in this example, some cable tray and some conduit right now. The conduit's over here in red. And what we have is an electrical example talking about placing home run conduit distribution, one inch conduit for every room in the building, right, to distribute branch circuiting from the electrical room out to the various rooms to provide, 4 to 6 circuits per room. And the question is, how do you get there from the electrical room? What elevation do you use to work your way across at a nice height so you can support all those conduits? And what we've built is the basic example of GenMEP is routing from point A to point B, getting around the obstructions as necessary to find a clash-free route between point A and point B. But building on top of that in Dynamo is running from point A to point B and then moving point B to a different location and running it again and then comparing it against point A route. So comparing many routes against other routes and finding the best way to get from point A to point B-ish, right, and scoring it and figuring out the best way to do it, right? Not just a way, a definable, benchmarkable best way to do it, right? So the basic way GenMEP works is you click on a straight piece of MEP system, and then you click on another straight piece of MEP system, and then we route between the two. That's point A to point B. It's very simple that way. Finding the solution between the two is not simple, but it requires users to place the start and target points in a decent location, basically, for the route to be something that's buildable. And so what we've done is open up our APIs to our routing engine, basically, to route between the start and target points, and then find the solution, and then do some math behind the scenes. Excuse me. So I'm going to walk through my different nodes here. I apologize for my mess on my canvas, but, you know, it works. So we have a couple groups here in the beginning that create what we need to route for a GenMEP, which is a start stub of system and a target stub of system. And I chose to put them in various places. So we're going to take a look at where those are located, and we'll run it. Okay. Let's just see here. So what we have is we are about to try and route between these blue points, right? So we have 40 routes in a grid, arrayed grid in the beginning here at different elevations, and we're going to test elevations of which way is the best way to get across the building at a horizontal plane. And these blue dots you see here in various places are the target junction boxes for home run routing. So I'm fixing the location of the target and just varying the start point to figure out which is the best start elevation for this test. So I'm going to unfreeze these guys. So we've got the actual node or actual group to make the junction boxes at the target points to make it look nice, and we're going to unfreeze these guys. So I feed in to this Python node here start and target information to basically say, hey, Revit API, draw a 1.5 foot piece of conduit between this XYZ and this XYZ to give me a start stub. And we can walk through that Python. That's where I get out of my element, is actually what's going on in that. As you can imagine, you read an example online and you make it work for what you're trying to do. But start to target stubs get generated, and then we feed it through the GenMEP routing engine. So we have some choices here. The routing parameters for each of these routes, we can choose the offset bend angle, right? So 45 degrees is kind of a standard electrical bend angle to use for routing. We're choosing to use 45, so we could vary that and input a list of different bend angles. You know, there's different options we can do, but basically this right here is the key. This node is created from the Revit, the GenMEP DLL that we include with our installer. That is basically the routing engine. You supply start and target points, and then routing preferences, and then output from that is solutions to the GenMEP routing engine in Revit. We just happen to make it an automated process as opposed to a manual process, the way that GenMEP works inside of Revit right now. Okay, so we're going to run it and see what we get here. It's easier with data in those nodes than empty nodes. So we're running 40 routes from various elevations, sets of 8 that work their way across the building, and we're going to get 5 different sets of scores for which elevation is best, basically.
Is this looking for classes now?
It is finding 40 different solutions. They're all clash-free solutions. So we are doing our algorithms through the maze to find 40 different routes, but they're all clash-free, so they all technically can be built, but which is the best way to do it is the question. So if you look, we have the way to quantify a route, right? One route has a certain amount of elbows or bends in a route. So each of these 40 routes have 7, 3, all these various quantity of elbows, right? And they also have a different amount of length. So if you apply a cost function to them, and I'm doing a very simple one, which is it costs $13.04 for every bend, and it costs $4.12 for every linear foot of system. Multiply that together, and for each of the 5 elevations, you get a sum, a score. Now, these dollar amounts might be in 2008 dollars. I don't really know, but they're comparable to each other generally at this point. And so if we look at these different scores, we say, I like solution set 0 has the lowest score here. 1674 is a low value in the score function that I built. Now, some people might say, cost per linear foot should be different, should be changed, and you can apply a whole different, there's a lot of special sauce that can be built into cost functions as well. So over here in Revit, you can see that the blue points were my start points. The elevations above the bottom one were determined not to be the optimal solution, so I deleted those routes totally, and we picked the bottom elevation and routed it for real in Revit and kept that solution. So as you can see, these 8 routes work their way across. Each one by one, they drop off into the J boxes as they hit their targets. So the scoring method, gives us a measurable way to compare different solutions. I can add more elevations, I can add more granularity and try different elevations. We're just limited by how many tests we want to run, basically, and how good of a scoring method you have. So there's a lot going on in this specific one. Go ahead. It finds routes. So GenMEP itself is a software product that finds its way through a maze by not hitting anything, using algorithms to basically work each route. We break the geometry that's obstructions in a Revit model. So all geometry that's in the way, we extract all that out and take a look, and then use basically video game algorithms to find their pathfinding way through the maze, right? And so we have linked models, IFC models, point cloud. And so we know the routes are good, but as you can imagine, there can be some crazy solutions on finding your way through a maze that you're not going to want to build that way. And so by putting a cost function to the elbows and length, you can really compare one route to another and kind of weed out, the outliers to say, well, yes, that is the wire can be pulled that way possibly, but that's not really the way it's going to be built. And so I want a pretty efficient route to get to the building part.
Clearance issues, just spots that can get through, but not very easily.
Yeah, I think, and the way that when we have those clearance issues, one route at a time, you might be able to get through, but as you try and do more and more, and you look at the electrical system as a whole, you might start filling up a certain area, and then all of a sudden a bunch of routes need to work their way somewhere else through the building. And so you're really gonna show it in your scoring method for the whole electrical system. Say, hey, the first 7 routes were really good, but then all of a sudden there wasn't enough room in this corridor, and we had to start squiggling our way through and over and offset and work our way around in some area that we're not supposed to be, and it's very expensive to be in there. And so it works in tight spaces. It'll find its way through beam penetrations, but
You can input those areas as like
obstructions, or remove them from the routable space, basically, but if you don't, the algorithms will find their way through, and it's shortest distance, basically, is the basic way we're trying to find our way through these paths. Okay, any other questions on this one? So I have 3 different MEP Dynamo workflows that I have been using recently. This specific one, I think we can really get ahead and put small electrical systems into a building much earlier than normal, because it doesn't take a lot of time to actually manually detail and draw these things out by hand and then have to fix it when other systems move, right? So you can actually run the simulation, put in your routing, and then next week when everything changes, run it again and figure out what the best solution is, and just have the solutions put in the Revit model as opposed to having to fix it every time and waiting until everything is more set in your models to actually model that MEP. Okay.
You said that you have a start point and end point, right?
Yep.
So why do you need to have those offsets at the start point? Where do those get you?
Let's see. Specifically in this example, they're going straight out of the start and working their way at that horizontal plane at 2'3" in the plenum, which I think is around 10 feet. So they're straight from the beginning, but then they hit that duct obstruction, so they have to go up or down. And so
So you're like, I see what you mean. I thought you were talking about at the start, you either like are at one point or another point, if you're like kind of
we go straight out from those start points, and we just run into something at some point. So I'd like to get over that duct, in theory, right? But the steel's in the way. It turns out in this example that there's not enough room above the duct and below the steel to work its way through that way.
So Ben, using the dynamo, defined all these points here, and then went through and fit tested every elevation here at looks like about a 3 or 4 inch iteration, right? And then we scored it again using dynamo to come up with the most optimum group, or most optimum starting elevation for this example. And so that may not have been entirely clear, but that all those things were happening when he was writing the script, and that was what the dynamo example did.
Validating those points first and then generating
Yeah.
based on what's
They have to succeed first, and then they get a score. And then the best ones that actually got a score compared to each other.
and your metric for that is then based on cost. So it's
It
like
costs-
which one is the cheapest,
Right.
and then that's the one that gets generated.
Right, but cost can be equivalent length calculations for, pressure drop. There's many different ways in other systems to score these things than just installed cost. I was using installed cost just because it's an easy number to throw at.
Probably,
Yeah.
Do you ever couple those together with other metrics? You can say, well, there's the cost, there's the route, there's the over under, there's other criteria that you define and then insert into.
There is the opportunity for a master best algorithm here, and we think that's part of the deal of internal company IP, because we are only 5 or 6 people, so we think that a company can build what is the best route for plumbing routes better than I can, because I can put 2 or 3 of those factors into a score and then generate the best, but having the ability to build that IP into what makes the best route and actually quantify it yourself is kind of, to me, a secret sauce piece that we can get to, easy level like this is easy cost, but
Can you show like the parts of like the more out of the box nodes of Dynamo that are working that then integrate with, I'm guessing, your proprietary nodes?
Yeah, I think we only had one proprietary node on it.
you want me to show some?
Yeah. Walk through
I'm
the
just
script.
curious, like
Yeah.
what's drawing in what your inputs and your outputs?
Sure, yeah. I'd love to talk
Well,
about
between I
that.
can
No
talk-
one
I
asks
can
ever.
talk about optimization.
Okay.
What we're kind of describing is what we call the on-ramp of optimization. So you kind of tackle optimization kind of a growing way. So if I have a point-to-point route, I can optimize one route. Okay. If I've got 8 of the same type of system, I can optimize all 8 of those. And this is an example of that, right? After that, you can then go, well, I've got 8 conduits and 1 duct, and I want to optimize those 2 systems to come up with this solution, right? And then once you've done that, you go for all the systems, and once you go for that, you go for the entire building to optimize it, right? So in that example, the good question is, if you had lowered that duct enough to get those 8 conduits over the top of it, that
Straight.
might have been a more optimum project solution for that example, or it may not have been. The traditional thinking would be that duct is expensive to move and wouldn't be able to go and do that. But if that had no cost to you, you could do it easily, then it would have a savings for the project. Right? And all those conduits would be dead flat over the top. So that's kind of, so we call it the on-ramp of optimization, how we're marching down that optimization path using things like scoring. So in my opinion, going after and looking at more complicated ways of scoring a conduit isn't as important as going and tackling how to score a duct and combining the two. Because that is more, then you get into a systems approach, which is more important than refining how you score a conduit.
Right. Test 4 aspect ratios of that duct against the same 8 routes at the same time and cross-multiply those options, and you have 200 different solutions you're going to work on. How do you figure out what the best of those 200 options were?
And so you can use Dynamo to do that.
Right.
You combine it with the auto routing and do aspect ratio testing along with scoring method to come up with the best solution.
Right.
And you could, that script wouldn't look much different from what Ben has written today.
So the actual dynamo-ness of this at a basic level, you tell me if this is what you want to see, but I don't have anything complicated in here. It's just lots of out-of-the-box dynamo nodes, list management. But if we want to talk about the target stubs that I drew in here with Dynamo are 1.5 foot stubs coming out of this JBox, right? So going from a Z value of 109.25 up 1.5 feet is, maybe 1 foot, is what we're doing here, right? And so if anyone has any questions on how this worked, but as you can see, I had to manually place the X and Y values of these start and target points just by taking a look at where we were in the plan and watching the points appear and then kind of fudging them around a little bit to get decent places where they should go. There's an automation example of how to make the best placement of these JBoxes as well, not just a fixed location of these target points. But these are fixed and they're hard-coded. But there's definitely some variables that can be placed in this part to get even more solutions to build. And all I'm really trying to do with this group, horizontal target points and horizontal start points, is build a group of points that are in the same plane in 2 directions with a certain length, and then have the Revit API using a Python node here draw a system between the two, because that's what GenMAP needs as an input. And it's like someone drew it by hand, right? Draw a little piece of system, draw a little piece of system. So the whole left half of this is just drawing a foot or a 1.5 foot long piece of MEP system in Revit at various places. That's it.
In the future, it should be a database call that interrogates, go find the JBox, go with my
Right.
single line diagram, find the connection between, or find where I have to go and find out where I'm coming from. And so that should really be a database call someday. Or a Revit database call.
Yeah.
You could probably find a way to select both of those test boxes or use those automatically get the location of those rather than manually entering them.
Yeah, the thing is, we need to know what connects those two. And so the junction box itself, a generic family, doesn't necessarily have what size and what type of system is connecting between the two. So Revit load information might be able to size the conduit automatically by, this is under 500 watts, so it's probably 3/4 inch conduit, or some number like that. But we need to know in general what Revit conduit families we actually want to connect from point A to point B. And junction boxes usually don't include that. Custom junction boxes probably could, with an electrical connector built into them maybe. So we can come back to this. I'm going to post this online, and I would like to hear any and all feedback about it. The scoring we'll walk through real quick. I think it's probably the most interesting part. So the proprietary node is this calculate route, which is generating the solution from A to B And then we have some two more custom nodes that pull a number of elbows and rough length from those calculated solutions, but not modeled solutions, right?
And to kind of talk about that calculate route, what that means, we're calculating the route without modeling it within Revit. Because if you model it within Revit, you get a higher overhead and more lag. So we're doing a fit to make sure that
we find a polyline.
And then use it to calculate.
We find a polyline and then we draw the conduit on top of that polyline.
Yeah.
So if we don't have to draw it, we can just use that polyline as a distance. We know every time it turns. Caesar, do you have a question?
So do you have to have the Building XP API installed in your machine?
You do. Yeah, you do. The other two examples I'm going to show do not require that, but this one does. But I think this is what we're most excited about, I would say. So again, multiplying, an elbow times a cost is easy using these nodes, and it's a good, decent example of moving math around here and finding the best solution. The last group here is, instead of just calculating the route, we want to actually model it in. So elevation 11, forgot to show that at the very beginning. So my Z elevations are 11.25, 11.5, 11.75. These 5 elevations are the elevations I tested. So route set 0 at 11.25 feet is the solution that worked the best. So at the very end, I feed that elevation in and say route from there. Use that solution and actually model it in, if that makes sense. Okay, and then I delete stuff. All right, so that one's good. Let me back out of this. So while we're loading here, so the next thing I would like to show is something that myself as an electrical engineer seem to run into a lot as a problem, is tracking mechanical, plumbing, medical, any kind of equipment that needs to be provided power by an electrical engineer, right? So you're sitting there waiting for documents and waiting for other trades and other people's information about where in the electrical world systems need, or a piece of equipment need power, right? And so let's keep moving through the design process, and it'd be nice if we could just wait till the very end and provide power when we need it at the very end to where all these medical devices are, for example, in this example I'm talking about here. But is anyone else an electrical engineer? Is anyone else facing that problem day to day about designing for other systems that need power? I mean, that's what I feel like electrical engineers, all we're doing is reacting to air handling unit loads. Water heaters were just added. Interesting. That just changed everything. That kind of thing. And so being able to it seems like a simple thing to be able to figure out where the mechanical or medical equipment is and make sure it has power, but doing that when there's hundreds of units and making sure it's always accounted for is what electrical engineers spend a lot of time on. Make sure that your loads are right, make sure that you have enough space on your panels, and it's all upstream from that basic problem of how many things are we powering and where are they.
Comment on the chat.
You're an electrical engineer. Somebody.
There's a comment?
Oh, just chiming in that we have an electrical engineer online along with John.
Oh,
There you go.
excellent. Tim. Anyone know Tim?
Thanks, Tim.
Thank you. So in this example, we have an electrical model with an M and a P and a medical equipment link in Revit, right? And so one of the things that I found in Dynamo that isn't perfect is that I would like to reference equipment through Dynamo from links. And so I found that you have to do some tricky things. I'm using, I think, Spring nodes to get elements from that way, but I really don't like using any modules that I can't use on a new computer fresh, right? I don't want to have to check dependencies, right? Yeah, I don't know if Python is better. It feels better because I don't have to install somebody else, but yeah, so I haven't run into Python problems, but I'm sure it's going to be a problem at some point. Let's see. Medical equipment, level 4. Okay, so in this example, I'm looking for a group of, a list. Someone gave me a list and says, everything in this list needs power, needs a receptacle, this whole building. For example, Med 101, our refrigerator 1382, those are pieces of medical equipment that need power. There are multiple refrigerator 1382 pieces of equipment in this building, and they keep moving. So find where they are, put a receptacle there for them, and then make sure it's always there for them as they move around the building in the design. And so it was frustrating to keep doing a lot of guessing and checking and saying, there's no master list of how many things we're looking to try and find. So I like this example, and I think, what are we doing here? Manage. I think it works pretty well for what it's trying to do. It's not algorithms through maze finding example. This is Dynamo core saving me time at work, right? So this is some basic stuff, but I found it to be very helpful. Okay, so we're going to read it in with our Spring node, right? So we're going to bring in all of the list of, what are we looking at? Specialty equipment from a link, specific link, link number 5 in this model. So we have a list of elements. What we're doing here is going to use Dynamo to put a receptacle at each XYZ of that piece of equipment. So I'm going to do that real quick, and then we're going to come back and look at it and do another thing here. So I like to have stuff in these nodes, talk about them. So we're just I'm going to run it for the first 5. I have a list, a CSV, for example, you could get from a PM on a project or whoever, even from the medical equipment guy, right? This is the list of the 50 device IDs that need power. So air handling unit 1, air handling unit, whatever it is, you can get a list from somebody and say, this is the list, this is maybe even are the loads of those devices. This Excel thing could work in a bunch of different ways, but this is just a list of things I'm looking for, device IDs I'm looking for, equipment IDs, excuse me.
Rather than going through a CSV file, would it be easier if the architect put in like a
Yes.
applying parameters or yes or no?
Yeah. Yes. I would love that, not only that the equipment has amps or horsepower or kVA included in the family, so I don't have to look at a table as well to figure out what the load is, right? I can read the load in from the same thing that I'm doing right now and work on putting that load into my disconnect family or my junction box family or whatever. But yes.
I'm an architect.
Okay.
It's easier to say if something's powered. You
Yep.
may not have a cut sheet, so you may not know the exact
Exactly.
power.
For a while, yeah.
But you could say pretty easily what's powered.
Right. Yeah, just a flag, even the yes/no instance parameter thing. I hope we didn't just lose it, but is usually the architect defining the location of these kinds of pieces of medical equipment. Yeah.
I think also requires a different mentality on approaching solutions for these problems.
Mhm.
Usually, you ask a traditional architect, they are conscious about spending more time that is required by
Right.
their contracts. And that's
Right.
to-
It's like, I need a little bit more time from you to tell me if it's powered or not, but it'll save me a lot of time on my end. And so, yeah, who's gonna really want to take on that extra work unless someone tells them they have to do it from the beginning, right? I guess.
Well, isn't it usually the major medical equipment, so RTKL or GBA would select the equipment, they put have their database and issue it to the database. The standard is to issue a spreadsheet.
Right.
Excel spreadsheet
Yep.
with all stuff.
Yep.
Some of the Reddit comments with like limited information.
limited information, maybe or maybe not loads, but hopefully at least this piece of information. Like, so in Dynamo, we're looking at the list of 50 pieces of equipment that I need to power, right? Med 101, refrigerator 793, refrigerator 1382, right? This list of 50. So in the beginning, I took the first 5 just to talk about it, to run it. So we have the first 5 pieces of equipment, but again, refrigerator 1382 is in this building more than once. So I have my list of equipment. This filter list for previously powered, I'll show you in a second because we haven't run this. This is a brand new time we've done it, but create list of instances of power, blah, blah, blah. We'll come back to that. But basically, at the end of the day, I find where, excuse me, I'm jumping all over the place. I find where those 5 pieces of, those types of equipment live, and it turns out there are 50 locations of those various types of Med 101, 1382, right? So the first one we were talking about was Med 101, and it happens to be, looks like 15 places in the building. There's a Med 0101. Has the same load, it needs a receptacle, but I have to track those down and hunt them and find them all day long. The second one I needed only 8, and then blah, blah, blah. Refrigerator 1382 had 3 of them. So what we put in was these 3 receptacles. They're not in the right place. They are floating. But where they got placed was the exact XYZ base point of the system that the medical engineer created, right? So this refrigerator, the base point happens to be directly in the middle of this 3D box. That's not where the receptacle needs to go. But if I know that all refrigerator families have an offset of, the width divided by 2 and centered on the wall, I can make this actually put it where it's supposed to go, right? But at the end of the day, if I know, if I have to come through here and move this around and do this, right? Now I know, I have confidence that I have all the refrigerators modeled and that's all I had to do, powered. That's great. And so what we inject into those receptacles that we need to power those pieces of equipment is the element ID, or the GUID, or whatever we want to talk about, whatever that number is right here. 1384516 is the device ID or the element ID of that specific refrigerator that we were looking for in the first place. So I pass through that information as a field into the receptacle that gets put in there. And now when I run it again, I say, so a week later I run it again. There is going to be nothing for me to find other than the 2 or 3 different refrigerators that got added. Because I put that GUID in there, I'm checking on step 1 to make sure I'm reading all the receptacles in here, and I want to know what SNL, the subscript 1 values are for all of them, right? And then if they happen to have a device ID, those get filtered out along with that name. So at the end of the day, I didn't put any more receptacles in round 2 because those first 5 pieces of equipment are already placed. So if I go from 5 pieces of equipment to 50, the full list, it's going to run. The first 5 are already placed, but you can run this every day to make sure that your receptacles are always matched up with a piece of, oh, that was faster, cool. So the second time around we put in, the first 5 were empty, but now we have 142 extra receptacles I just got placed in all over the place, and they have the device ID of the host piece of equipment, and they have this little special flag that I put in there in case I want to delete them all in a group. It helps a lot to have confidence that you have a receptacle for each piece of equipment, and not to mention you can keep the circuiting and run this again. It doesn't destroy all the electrical things that happen if you need to keep the receptacle in, and so you can circuit it along and not destroy the whole deal. So I'm not sure if anyone has done electrical circuiting in Revit, but you can't swap in a piece of equipment after it's been circuited. It kind of throws it all into a loop. But you can move it around. All basically we're doing is looking for that device ID in that comment field.
So part of what you're doing is you're doing auto-populating of receptacles based on the list.
Yeah.
And part of what you're doing is kind of a change management type of
Right.
packaging,
If I run this again, we're not going to find any changes. But the link changes next week. I can run it every morning, and it'll tell me, hey, I added one receptacle. Here it is, by the way. You should go take a look at it and make sure it's on a wall.
So the adaptation of the script would be to add in being able to find the closest wall.
I would love that, yeah.
And then put it in a preferred location.
Right. And the optimal elevation for each piece of equipment. But, yes, there's more to it. And even adding, if there's a unique keynote to each of these pieces, a note that we want to add to all fridges for some reason, or a tag that says plus 46 inches AFF, those can be added with, specific information about each of those. We can pass through load. We can pass through a bunch of information to those receptacles to keep it synced up. Ever?
So if with the design and the way that the family is actually built help with placing that initial device on the insertion point?
It would. I think having a...
If you have to come back and you hit space bar, if it was at, say, like the back of the equipment and already near the wall.
Right.
I can just select and go flying through it.
I'm not sure if I can ask the medical equipment people to make the family base point in the right place. I would love to do that, but one thing I would like to know is which way is the medical equipment facing, and I think Dynamo can do that as well. Like, what is the vector of the front of a piece of equipment? I think you can read that in. I was playing with that. It's not in this yet, but that's a further thing too, is at least let's get the receptacles facing the right direction. But having them not face the right direction and not be on a wall really helps, because then you're going to sweep through your project and you can fix those things. If they're slightly close, then they could be off and you're going to leave it. If I could make a big happy face family to say, this needs change to a receptacle, fix it, because it just got inserted, right? So it doesn't necessarily matter what family you put in here. You just need to be able to find it and make sure it's looking good. If it's perfectly optimized and it sticks to a wall, that's great. But the big amount of time is counting how many of these things do we have and where are they, and did somebody move one, or did one get deleted, or those kinds of changes that happen all throughout design that I want to, like I said, just wait till the very end to actually put the power in for these pieces of equipment. If the equipment moves after I've already run this once, the receptacle won't move at the moment. But a rule that I think would fix that is the receptacle within 3 feet of the source, for example, right? If so, if not, flag it or delete it, or do something, right? So that's the rule I think that would fix that problem. But right now, you run this, then the equipment moves, the receptacle is going to stay over on that wall, and it's not going to be near its friend, but at least you'll know what it's trying to power. It'll have that device ID, and you can say, we could even have it draw a red line between the receptacle that was placed and the element ID of the thing it's trying to power. And you can notice, hey, this is like way over there, and these other ones are, visually or something like that. So there's a lot of different ways to check that. And I don't, I tell myself, you only have to do this once, and then you can do it on every project. So it's probably worth the time in building and building and building and making it work perfectly. But this is a pretty new thing, and I'm liking how it works right now. It's not that complicated. I think the only node that I'm using is the Spring node to get the linked piece of equipment in. So, yeah.
How many hours do you think that how much time do you think you save on the future, on the project? Because I'm guessing that people who use Dynamo are probably within their firms trying to justify their time a little bit.
Right.
And, it took time to go and write that, but how much time do you think you probably saved over the lifetime of that?
You probably save at least a half a day per floor, per 50 piece of equipment, I would guess. So this project that I'm looking at here has 6 main floors of equipment. So every time you run it, throughout the life of the project, maybe. So that's only one time though. Every set. So at 100% DD, you have to run this and make sure you covered all your piece of equipment. You run it again. So it's probably 4 hours per set per floor, as my guess.
And so the same logic could be extended to any type of fixtures, basically.
Oh yeah,
right?
yeah.
Signs or security devices, cameras, or ceiling mounted.
At the end of the day, we want architects to tell us where everything goes, and we'll just read it in, and then we'll just automatically place it there.
But it really lends itself towards a data-driven approach.
Right.
Kind of have the data, and if we store the data correctly, we can do things like automation to make sure that we don't.
Well, if architects are placing light fixtures, right, and we link them in, then we have to try and bring electrical light fixtures on top of it. Why not read in the architect location and automatically place them exactly where the architect said they were going to go? I mean, and that, it could be done for light switches. There's a lot of visual things that are important for specific location that needs to be put in there. As long as we're talking in the same language, we can follow those things around.
Can you also apply that we read the tag information and then we go to the Excel file to find the power that we need to provide and then we input back to that receptacle?
Right. Yep. Yeah, I mean, so this Med 101 has an amp load on it, this family. It's not great, and they're not necessarily in electrical. Yes.
Like even though their equipment has no parameter for that, we can still use Dynamo to read it.
Correct. Or even equipment schedule, or the manual way that on those cover sheets the equipment schedules are listed. As long as we're talking about Ref 1382 and there's a line in there, we can use that as the key to everything, right? Whether or not it's in Dynamo. And so, yeah. It can be the key to the whole piece of equipment. If we're all talking about 1382, we'll pull it in from multiple sources. We'll give it the load, we'll give it the location. Revit helps with the location. The load might be in some unique Excel file, but if we're talking about the same key value.
Matter to the location of the receptacle.
Yep.
And I know the default is 156 inches.
Yep.
The receptacle. So that might be another issue, another solution to read the information and placing the right elevation. You don't have to worry about the elevation and the power you need to provide, and then you go to each receptacle and modify the instant parameters.
Right.
Like one by one.
So at the end of the day, I'm just trying to make less work for electrical engineers, it seems. I can say, hey, plumbing guys, can you at least tell me if it needs to be hardwired or a receptacle plug, right, to power a thing, right? So that can be a parameter that can read in for equipment as well. Is it hardwired? Is it a receptacle? And that helps me automatically put in a family. But the plumbing people are looking at the cut sheets, so they don't need to put it in a table and tell me this necessarily. So it's again the data-driven approach. You read it in, and if we're talking about equipment that I don't own, the engineers that are specifying it can really own it and get exactly what they need from it. And if there are questions, we can work together on it. But I just feel like it's a pretty helpful piece.
Can I maybe make, I guess, an observation from my experience? So, things like light fixtures and features and door hardware, things that need power, usually come from different sources. But I think medical equipment, usually people are specifying that, pull that from the database. So they go through the list, the program, and then pull from the database and then populates the spreadsheet. So I think in terms of opportunity,
Right, it's all there already.
if you can work that, it all comes from a database that we select
Right,
that piece of equipment. So I think,
but that,
GBA doing that too?
we have a part of the ZEDI. We have a GBA. We have a software planet. So we're developing that.
does that get all the way down into the Revit families generally, or does it stop at an Excel spreadsheet usually? That database dump.
I'm not sure, to be honest, Charlie.
Okay.
Do you know?
I can check.
Yeah.
Yeah, I think if they have database, their value scale is really high end. So it should be also associated with the family.
Yeah.
too.
As long as it doesn't have some weird parameter in the front called medical _ amps or something weird. But we can pull it, we can find it. Whatever way we're talking about it, it's fine. You should have to tell us what the field is called. Okay. So I like that one a lot. I think this will be really helpful. I'll post it online. You can play with it. I think it can apply to a bunch of different things.
How does Plenum delete elements?
If I delete this and run it again, it'll add another one right for me.
If the architect deletes it.
If the architect deletes it, I don't have that failsafe built in. Let's see.
You bought an extra outlet.
You bought an extra outlet, but again, it would just be as easy as saying, "Hey, what receptacles are in this project that don't have a matching host?" That's easy. Turn them green, turn them red. Yell at me and say, "Hey, by the way, these 6 things dropped out of there." I don't have that in this right here, but it's the same beginning script. It's saying, look at all these, match up the source device ID with what's actually on that receptacle. If they can't find a friend, then there's something going on, and take a look at it.
In some kind of index to the populated that we're referencing to those pieces of equipment?
Yeah.
At least compare those two lists and know that they don't match.
So I don't have enough fields, but I would love to have. So right now I'm showing subscript 1, subscript 2. Subscript 1 is showing the actual, like I said, the GUID or the device ID, excuse me, the element ID of the source, the Med 101. If I had a third field, I might say Med 101, right, like the actual name of the equipment, right? If I had, which I just don't have in this family at the moment. I didn't, whatever. But all we're doing in this beginning, this group right here is saying, read in all the electrical fixtures. Let's take a look. Let's take a look at subscript 1. Let's bring in all these element IDs, and then we're going to, does the list contain item, and filter it out, and then we get our list of stuff that we need to actually work with. In this example, there's very few because they're all already in there. But yeah, I mean, the filtering, this group is kind of the key on doing all these things about, did something move? Is it within 3 feet? Did something get deleted? Did one of our guys delete the receptacle and it shouldn't have been deleted? That kind of thing.
Did you also make the receptacle to be non-hosting family?
Yes, that's helpful. Yeah, I don't want to deal with hosting ever. I haven't found a good reason to host, but maybe hosting would help me stick to a wall, or like, I'm not that good with families, so maybe there's a way to have them stick, but turn and stick, I don't know. But I don't mind doing the manual way of doing this and getting it on a wall. Like I said, if it's floating, that's okay. Okay. So the good news is I don't have to run this one. It already ran because it takes 20 minutes or 10 minutes, I think. And it takes all my RAM because I have a huge memory leak on this script, but this file. But what we want to talk about is the idea of complexity in a building above a plenum. So I'm going to give you the secret look there, but really what we're talking about is the same building we talked about before, right? So above the ceiling, there are these ducts and there are these conduits and there's stuff going on. And we had the idea of building a way to measure complexity by a basic way of what is the volume in a certain 1 foot by 1 foot area. What is the volume taken up by an MEP system versus the extra space in that area? So is it 97% clear? Is it 50% clear? And so I'm going to show you what I mean here.
People know a conduit fill. You have a conduit, you fill up the conduit.
Where is it?
With wire. There's a ratio of fill to open space. We're doing the same thing, except for the area above the ceiling, in order to go and score how complex a building is, both within a given room and for the entire building, as an example. So if you're going off and building a hospital, the hospital is going to have the highest, probably, complexity score over the entire building. If you're in a school building, you'll have, like a school lab, for example, you'll have a whole bunch of complexity in the corridors, but when you get into the classrooms, it'll probably be a little bit better. And so what we're doing here is we're showing Ben wrote a Dynamo script to go through and characterize the entire building floor plan for complexity. And kind of the background of why we're kind of doing that, the problem that we have as we go through MEP coordination is really related to how much stuff we put up in the ceiling, right? And so if, I don't know how many people have been on a project when you're going through design, and you're going through planning and coordination, and all of a sudden the owner goes, hey, I hired a low B guy, and you know where the cable tray is going, right? And so using this type of example and showing that map of what the complexity looks like, you can look at how the building adjusted to adding something like a cable tray late, or a fiber optic line late, or looking at why a corridor is particularly hard to go and coordinate. So that's kind of a little bit of background of why we're doing that, and kind of after Ben's done, I can tell you where we're taking this and where we're kind of going.
So this is the result, right? We call it a heat map. So if we look at the plenum space in a building, we can start looking at pinch points where there's a lot of stuff, volume of stuff in the way, or just not in the way, just there. Where do we need to start really focusing our efforts on coordination early, right? Each one of these 1 foot by 1 foot boxes here, I have them all over, has a complexity score associated with it. And I'm going to show you what that score is, but it's really easy and really simple, and you'll be surprised. It's not rocket science what we're trying to do here, but you can see some of these are green and they have nothing in the way, right, down to the ceiling. Some of them are red, they have duct or other stuff. Some of them are light green or a little darker green, they have a little bit of stuff going in the way. And so what we're doing is using spring again, because I need to get my links, my duct from my link. So we bring in the ducts from my link, and I have conduits already in my native electrical Revit model. We bring them together here, and we filter them out just on level 1 to make it faster. I don't want the whole building. And we have a list, right? And we make solids from the Revit geometry of the MVP systems. Then I want to build a scoring column, basically, create Plenum Solids. And what a Plenum Solid, I call a Plenum Solid, is this thing. These are Plenum Solids, 1 foot by 1 foot by 3 foot tall columns of geometry. So I want to make that at the proper spacing of this building. We can take a look at what happens when you try and find the intersection between all the geometry on the first floor and those columns. You get a certain amount of space that's taken up as intersection space. And I think this is pretty cool looking, so we'll see how it looks. Those columns get chopped into pieces. So we have ducts and little pieces of conduit and everything else in between, broken into 1 foot by 1 foot cuts from the top, right? And where we take that is add up the volume on a column by column basis and divide it by the total volume of the column gives a complexity score. So if we're looking in this bottom left corner, this round duct has, it looks like it's intersecting with 2 different plenum columns, right? So you can see it's cut kind of in the right third. And hey, stop. Okay. So I'm using TeamViewer because this laptop doesn't have the RAM for this idea. But, so complexity score, we create the geometry intersection points, we add them up per column of plenum volume, and then we create a complexity score, which again is intersected volume divided by total volume. Total volume happens to be the same number for everything, right? Because they're all 1 foot by 1 foot by 3 foot things, and but if we look at complexity scores, they're on a 0. These are percentages, right? Percentage full, and we take that percentage full per 1 foot by 1 foot grid and feed that into some more Dynamo nodes over here that do color on top of Revit families, right? So it's not super complicated, but it is very interesting to look at the changes that happen in a project as complexity, as more systems get put in the way. I'm going to bring up this one. We'll take a look at both of them. Hey now. I don't know what. Hey now.
So if the architect has raised ceilings in certain areas, does this detect it up?
Right now it's really manual to say, but yes, it could. Just by the bottom bounding of those columns can be changed and should be changed for different ceiling heights. The way we really think about it is maybe a user would create a Revit space from the drop ceiling to the floor slab above in the whole plenum area, which can, those heights can vary, right? I just want to chop that into 1 foot, 1 foot grid. I don't care what the height is, and the math will change, right? The volume divided by the total volume of that column will be variable because the column is kind of changing. In this example, they're the same.
Okay.
But yeah, you would create a Revit space and then chop that up into 1 foot, or even more resolution if you want it.
I can talk a little bit about where we've kind of taken this and kind of adapted it. So Ben has written in Dynamo kind of pseudocode or code in Dynamo. And what we've done is we've then taken that code and converted it into C#. And so over time, this will change quite a bit. So for example, one change we've made is the green and the red don't make a whole lot of sense without a third color, because you can't really tell. It either goes really green or goes really red really quick. And so we need kind of an intermediate color of yellow to kind of really be able to distinguish between where it kind of varies over the course of the floor plan, right? So that's one change that we've made, and then we're also doing that to be able to pick up where the ceiling height is and kind of pick up where that gig goes, as well as being able to refine the resolution so that if you can run it overnight, and it'll take a couple of hours, but you can get it down to a 2-inch as opposed to a 1 foot resolution, and be able to go and track that and be able to look at that. The importance of really what this is, though, is what you're looking at is the beginning of machine learning applied to clash detection. Because with clash detection, we're getting too many clashes, and we need to prioritize them. And one of the ways that we can prioritize clashes really well, clashes that are happening in a high congestion area are a higher priority because they're harder to fix. And so by doing this type of work and being able to come up with a complexity, we can back in to being able to prioritize clashes in an algorithmic and computational way, as opposed to the way we currently do it, which is kind of by our discretion. So that's why we're kind of working on this. This tool, as you kind of see it now with those improvements that we're making, will be distributed as freeware to the industry, because we have a sponsor who is helping us to advocate and promote this type of thinking, where we're thinking about the complexity of our buildings and tracking it and telling stories about how complexity changes as we add and make it more complex. And so you will see this as a freeware piece coming out from us in the next couple of months.
So complexity is interesting, though, because electrical conduits don't have much volume compared to a duct, right? So I've been talking about volume divided by volume, right? So complexity of a bunch of conduits compared to one big duct doesn't seem to add up to how much trouble that is to move them, right? And so there's something to be said for weighting the volume of certain systems, because we know each electrical conduit probably needs supported, or a plumbing system needs some support, or needs some, basically it's not just the volume is to create complexity. It's a basic way to score it, but again, just like comparing a route between A and B and scoring it that way, there are many more deeper ways of scoring this than just what I just talked about. This is the basic, this is scratching the surface, and I think there are smart people that can develop better ways to think about complexity than just this, and have a whole different way of visualizing this and saying 2 conduits and a duct is red, 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 bad, fix it. Like, or, that's going to be a problem. Or P-tube, it can't move. It has a huge complexity score, even though it's small volume for some reason, right? And so there's ways to throw some weights on these different values to make it look a little bit different.
So maybe we have a baseline of congestion of how much fill you put in,
right,
and then we modify it by the type of systems that are in that to get to a higher score or a more complex score. Another example would be if you have a volume and it includes 5 clashes, clearly that has a high complexity because it has these problems with it.
Right.
And so you can modify it. You can modify it again with the number of clashes that it contains in the volume as well.
So the second and third thing I've shown today are you just need Spring, which is public, and so you can do these things. You can run it already. The first thing has the first example I showed had GenMEP, which is what we are working on developing. So I'm going to post these, and you can play with them. I would love to have questions, and I would love to talk about this more.
a ramification of this type of thought is doing it the opposite. Build a topology of potential congestion ratios that you can use in early planning
Yep.
to know what are the areas you need to focus more.
Yep.
And so by having this nomenclature of potential congestion
Yep.
routes, then you don't have to wait for all the geometry to be placed to find that out.
No, you know,
you
at
plan for
DD,
that.
you know that a complexity of 30% is a problem. It is not going to work in that corridor. The 300 projects we've looked at with a complexity of 30 at 50% DD means we need to change this now because it's going to be a problem when everyone gets their strut in there and their supports in there. We know that this is on the edge or even past the ability to coordinate. And you can do it early and you can do it when there's time to change some of that area, as opposed to at the end when you have to really spend a lot of money to fix that problem. That's my favorite part, is early fixes of not having enough space, or we can give space up. Oh God, we can give space up for MEP in the beginning when we know it's not going to be that complex later, possibly, right? We could let ceilings get higher because we know that area is not going to need it. Now, I know that's never going to happen, but
Well, and a contractor should price their work higher if it's a highly congested.
right,
And by the way, they can get the money back if that tick lowers soon.
right.
Because it's all, if it's tightly congested, it's hard to do it. So I think that there's a lot of thinking we can go and do. And part of that is the machine learning, because every architecture firm and group of people are going to have a different approach in how they develop the building, and how it kind of goes. So if you have one firm, they might have a fairly low congestion at 100% DD because they wait to model late,
Right.
or vice versa. You need to be able to account for all that and kind of measure it.
So a couple of questions. I'm not sure how it relates to this. So I guess when you relate it to real world installation. So certain systems have a higher cost of moving them, with higher cost of challenges, things like fire protection. And then the other question is things with other systems are more flexible, like big routes of MC cable. Those are the sort of things you're considered in your algorithm, or how do you address that? So I'm just thinking about the workflow of actually doing coordination.
The interesting thing we think is not the score, but the change in the score, because that tells a story of what's happening with the building and how you're coordinating, right? So I think that's kind of the distinction between looking at that volume number, right? Because you really want to, if I show you this right now, and with the more colors, it'll be more vibrant and more tell a better story. But if you look at one and you go, hey, here's A, and then by the way, 2 weeks later, here's B. Look at how the building fundamentally changed from A to B from a congestion and constructability point of view.
So one use case I was thinking is where you locate the electrical room, right? So typically it gets put between the elevator and the shaft because it's just programmatically that's the place to do it. But it basically means you have this one window to get out. So I guess it may be a use case is if you with these electrical rooms that say laid out in a configuration, do a heat map. I guess there's like a heat map.
Or if you put it in 3 places and see what the heat map looks like,
Yeah.
basically, and put it there and then route between everything and then see how complex, which is the least complex area to put an electrical room in to make that choice.
Is the engineer, here's this, here's where you make it work, whereas if you do the heat map, I'm just thinking, quickly run that and you get a visual indication of best value.
I think it helps explain outside the trade of what you're thinking about, right? Like electrical feels congestion, and you're like, look, I think I'm showing you this congestion in this way, and I think it's a better way to explain it with numbers as opposed to saying that corridor really feels like it's not going to work. You know what I mean? And you could say, hey, look, it's 75% full on average.
Is there a way you could build in like a factor for the different trades in per capita?
Yeah, if you have 5 trades in one box, that's more complexity than one.
Yep. Yep.
Yeah. But there again, you kind of have, there's difference between congestion and complexity. There's a fine line between those two. And if we provide the congestion, the ability to go and measure congestion within a building, and you as a firm want to come up with your own complexity score, you could use Dynamo to make that score. Is one way to think about it.
So with the data and story that heat map tells, that should give me a little bit more hard evidence to maybe go to my team internally and say, well, hey, like Ben was saying early on, let's stake our claim, our space, so that we know from the get-go that we're trying to optimize our route out of there,
Mm-hmm.
I find that a lot of the time, we don't get a chance to talk internally because we're already starting to deal with thousands of clashes and other change management. But this gives you that hard evidence, like facts, to kind of put that at the front of the conversation, so to speak.
Yep. Another example would be being able to route conduit within the deck, in the concrete, or not in the deck, right? Because you put it in the deck, you lower your complexity, you lower your congestion because you're out of the area, and then you can quantify that with numbers now. So I want to have time to go and show you and get your feedback, or show you so you can get back to me and give me your feedback on.
On this.
Yeah. If you go back one to.
This.
Yeah. Okay, so we have this program called ClassroomMP, and I'm going to show you what ClassroomMP does. And we want to integrate it into Dynamo. The integration into Dynamo is not hard to do, but we want to find out how you guys want to use it and what you're going to do with it so that we can make sure we're giving you everything that you want to come out of it. So here you have Revit, and ClassroomMP does real-time clash detection within Revit. And so here we're unlinking or hiding the mechanical system here, and then we're drawing in a cable tray and looking at the clashes, and then dynamically declashing it here as you go, right? And so there's your cable tray, and you can see down here below in the table there's a list of all the clashes that cable tray hit, and we're graphically showing it on top of the plan within Revit. So that's a clash with, it looks like a duct, and that's a clash with a unit of some type, right? And so the question we have for you is, how should we tie that into Dynamo? What do you want to be able to get out of Dynamo using this type of thinking? Because we know that you're probably going to want to take that clash item and do something with it, but we can't predict what you want to go and do with it, right? So
you just change the elevation of that.
Yeah, so that was an elevation change. You can see that it's into the ceiling because the entire thing turned red. And then we're going to raise it up until it clears the ceiling, and then we'll adjust the cable tray down.
So Dynamo already could iterate over this elevation until the clash is less, right?
I don't think that's the question. The question is, what do you want to do with a clash event in Dynamo?
Can I use this in conjunction with JMP? That if I have a clash, that I want Dynamo to go and break before and after, and then use JMP to run my start and end target over that structure.
That would be one. So what information do you need from us to be able to do that?
And thus this information is feeding into Dynamo and then generating a basic heat map. And then you can start moving this towards the cooler areas. But in some ways, like once you've gotten to this level, like the end result maybe shouldn't be Dynamo. It seems like Dynamo is like that great like setup for figuring out what you want to do. But once you've like coded this, and I think this is what we got out of our last meeting and kind of this discussion on like programming in C# is like eventually you're just going to write the program that just starts to do it.
Yeah, I think you're right. But we want to take advantage of people out there in the world who know Dynamo, right? Because you don't want to wait for us to go and code stuff.
see what you're saying. Yeah.
right? So we want to provide the API that gives you the ability to connect that to Slack and have somebody go and take care of a clash, and it informs somebody to Slack to go to Trello or whatever it is.
Right now, these fields are not queryable, right? I mean, the point is that we can open these fields up to query, right?
Well, I mean, I guess what we're really trying to do is how much information do you want out of that, or what information is important, you know?
Yeah, the where and the how much, I think that for that information, you can unpack that in a way that you can start feeding that in. Otherwise, you don't really know what you could do with it. But the more that you can, take from it, like if it's generating a spreadsheet, that's one way that you can have some interoperability with Dynamo. If it's like actively writing something that's then actively being read and then running through something else, I mean, that's the part that you kind of have to discover once you have it in front of you to some degree. But seeing the clashes right there, you're just like, oh yeah, well there it is, I'll just deal with it because it's right there. But if you're trying to say, oh, I want to dynamically then change my ceiling height and maybe run that kind of like scoring like you were doing in your routing, and say, well, if I'm lowering the ceiling height, it does X, Y, and Z, and that's something, that X, Y, and Z is something that I have in my Dynamo script that's being informed by
Quantity of clashes, size of clash.
So maybe I'm thinking of it wrong. Maybe, do you think that what you really want, you can use Dynamo much like Ben does and do a test fit of that cable tray in every part of Plenum? You can do 1,000 times per Plenum.
Possibly, yeah.
And what you really want is you want a list of clashes that come back from whenever you go and run that. So, okay.
But you don't want to remove the human element, right? Like coordination still requires that we talk and work with each other to try to. Once it gets all automated, how do you ever go back to?
Yeah, we're definitely not there yet. So
I think there's too much end user variable. Like what is your building used for? What where is it located? That is going to determine. You don't want it just automatically moving and changing things. Except maybe that you could tell it. Hey, I want these items to have priority, but that would be on a. You have to still do that on an individual project basis.
But I think it's better for you to do that customization than
That's
it is
what
for
I'm
us.
saying.
So we want to provide the API for you. Is our near-term position on it.
I think when it comes to clearing the clashes, one of the things that sometimes is missing is given a way to establish what is the right sequence of construction that is going to enable that to work. Something could be clash-free, but it can be not constructible at all because this is the different detailers are not going to know how to put it together. So the person who had that criteria are people on the field. So if there was a way to extract this and somehow incorporate in a way of scores or something that identify what is the right sequence in order to make the decision of what moves where, then that would be a much more informed way of clashing, clearing the clashes.
Yeah, my opinion on that is that, the human element is huge in all of construction, all of artificial design, right? And if we get faster at modeling and being able to show a complete workable picture, people in the field can have more time to pick it apart and tell us what they really want. And then we can adjust it and go and look at it. Because right now we're not providing, when we go to the field and show them what we're doing, we're not providing them with the whole picture of what actually is workable because we're not getting to a coordinated model until very late. So we're trying to get to a coordinated model quicker so we can get feedback on what you're saying, which is there's more to it than just being clash-free. So that's my kind of take on it. I don't think, we're not, so that's my take on it. The field, every field group is going to have a different opinion about the proper way of doing that, and we can't change that. We're not going to prove that.
Yeah, what I'm seeing now is a search on design build deliverables, and we have the contractor giving us early feedback on how our system needs to be routed. And so that communication between what our designers are doing and the point at which 50% DD, where we get the feedback from the people on the field, is not really clean.
Yeah.
And so there's some information that we could harvest in the design to make that.
Yeah, there's always going to be that kind of workflow question. I think there's kind of this still assumption of the kind of, design, bid, build scenario, and like we're trying to respond within that kind of workflow. But I think what we're getting into with more data-driven solutions is we're actually pushing more towards an integrated project delivery argument. And until you get closer into that, where you have much more information up front, do you really see these type of things like take off and make the kind of effect that they do? But we still have these kind of like gaps in like throwing information over the wall and like responding to them, and they're not quite integrated yet to where we really can keep the ground running with some of this stuff.
But
I've
all
seen that too, with contractors asking for a lot more, a lot earlier. And so it's kind of behooves at least the architecture side to be more able to provide at least a higher level of information so that people can respond to it and make these kind of data-driven solutions more effective.
I think that the great thing about BIM and automating BIM, including with Dynamo, is that you still have the opportunity to go and make changes and be able to affect the things that you're talking about, because it's early enough in the process to go and do that. And if the tools get that much better and more responsive and we're able to model quicker, that just makes more of an argument for IPD, because the field personnel can really give more feedback and make it more responsive. So I think we're about out of time. So there's Ben and my email addresses. You can spam both of us with any questions you have. Ask for code, get code, whatever you want. And then our website is there, so you can grab stuff from there. We also do a whole bunch of writing. If you go up on our website, there's a whole bunch of writing we do about BIM, because we really try and advocate for BIM people and BIM processes, and so we write a lot about stuff there. So, and with that, I think we're done.
Great. Let me see if there's any question on the. Nope.
Our Italian friend.
Alberto, we work with Alberto. He's great. He does call me at like 3 in the morning.
Well, let's give an applause to these guys. And thank you. I'm going to post these on Friday, so we're ready by next week.
Thanks, guys.